All right, so before we move to continuous time models, maybe let's just write down once again the problem that we ended up for the principle in the second best version of the problem, so that we can see again where things were starting to become complicated when we were in the static case. So if you remember from this morning, what I had written was that this, the value that the principal was getting, could more or less be written as follows. You were maximizing over contracts, and then we had the complicated part here, which was maximizing over efforts that were optimal for the problem of the agent, right? And then here we had whatever value the principal was getting. So this here was one way to encode the incentive compatibility condition that I had given you, and that was exactly what was problematic in the static case, because we were saying this incentive compatibility condition, we don't know what we can do with it, and basically the only way out in the static literature is to just say, let's simplify the constraint, replace it by the corresponding first order conditions, and pray that that doesn't change the problem. Right, so this is understanding what is the structure of this set here. That is a hard problem. So understanding the structure of A star of Xi is somehow at the heart of the problem here. So this is something that we had trouble with in static setting. Doesn't change much. I mean, it's actually even worse if you start moving to dynamic discrete time. And most of there are papers in dynamic discrete time in that area, but more or less what they do is just almost a sequence of independent one-period models, right? So if you already don't know how to solve the one-period one, you're not going to be able to solve the more general cases. So the great thing about moving to continuous time is that in continuous time, we will understand much more easily what this set actually looks like. All right, so let me illustrate this. And you should realize rapidly once I write down the problem that understanding what this set looks like is just a matter of applying what is usually called the Martingale optimality principle, which is a way to characterize optimizers in some optimal stochastic control problems. All right, so what I will show you is the first continuous time model. So that's due to Holmström and Milgrom in '87. So it's really almost the simplest continuous time model you can think of. And it's going to be the continuous time version of this example I gave you this morning when we were taking the distribution of the output as being Gaussian. If you remember, I told you, yeah, so if you move to continuous time, instead of having this Gaussian random variable, we will have Brownian diffusions. Right? This is exactly what's going on here. So, as usual, so here I start now with a probability space omega fp. This carries, it's a one-dimensional Brownian motion. and F is the P-completed natural filtration of P. So if you remember what we did in the static case, then I started by defining the output, okay? And then by explaining to you how efforts made by the agent were having an impact on the output itself. So the output, now this is simply going to be xt will be sigma bt for some positive sigma. And then, of course, now, what we were doing in the static case was when the agent was choosing some level of effort, that was changing the mean of the Gaussian random variable. So here what I want to do is say that when I make an effort, when the agent makes an effort, this is going to change the distribution of x. Now, right now, x is basically a Brownian motion. When the agent makes an effort, I want x to be a Brownian motion plus some drift that's going to come from the effort itself. Right? And the easiest way to do something like this is to use Girsanov's theorem and define a probability measure equivalent to P over there, such that under that new measure, x is going to be Brownian motion plus drift. Okay? So efforts for the agent are now, let's say, R valued, F predictable, process is alpha, and because I want to be able to do this change of measure, there is one condition that needs to be satisfied by my efforts. I need enough integrability for the new probability measure to be well defined. So here what I need is that expectation of the exponential of, so that's, should be plus, integral 0 to capital T. Yeah. Right, so I want to have this. So here there is a new element I haven't talked about yet. This is capital T. So capital T is going to be a fixed time horizon, and that's going to represent the length of my contract. All right, so once you assume this, we can define a probability measure P alpha on our original measurable space, and such that the Radon-Nikodym density of P alpha with respect to P is exactly given by the quantity over there. Right, so that's, yeah. That's on F capital T, but yeah, I don't care about anything that's happening after capital T. right, so this is exactly what I need for this to make sense. Obviously, this was not happening at all in the one-period model. In the one-period model, I was only making a choice for alpha at time 0. It was a constant, so any integrability that I want would be satisfied. Here, things become dynamic, so I have additional restrictions. All right, and then let me give a name to that set. That's going to be calligraphic. Okay, so now of course we know that by Gersanoff's theorem, if you take any alpha in that set, you have that. Now you can write the output as follows. So now this is a Brownian motion here, B alpha. And B alpha is simply original B minus the integral of the drift. And we know that it's B alpha here is a P alpha Brownian motion, right? So that does exactly what I wanted. Agent is choosing an effort. This effort generates a probability measure, and under that probability measure, the output now has a drift that is immediately given by the effort. So more generally, of course, if the only thing I'm interested in is changing the drift, I could put a more complicated function here that still works exactly the same way. But I mentioned that a little bit later when I'll tell you somehow how far you can push this approach here. Okay, but so far this is really the strict equivalent of what I showed you this morning. So once you're here, what we need to define are the objectives of the agent and the principle, and it's going to be just one of the cases we saw this morning, the multiplicatively separable one, where everyone has exponential utility functions, okay? So here we assume now that contracts, therefore now F capital T measurable random variables So here, what does it tell you? F is the completed natural filtration of B, so that means that those things are functionals in general of the path of B. So this is my notation to say that here I'm looking at the whole trajectory of the Brownian motion all the way to capital T. But I don't really care about B here. I care more about X. The good thing is that it's probably still somewhere. Yes, X is just sigma times B, so the filtration generated by B and the filtration generated by X are exactly the same. Okay? So here this is the same as saying that taking functionals of the path of X instead. Okay? So again, exactly the same thing as this morning. Contracts were measurable functions evaluated along the output. And here, same thing, except that my output now is a process, so there is something that's dynamic. So in general, I should just allow all of this to depend on the whole path of X, all right? And they will belong to some class C. So this morning, I was telling you that I was going to remain vague about what C was, because yeah, sometimes you may need some sort of topological structures on the functional and so on. Here, I'm also going to remain vague, but for very different reasons. Basically, what I need to put in C is integrability conditions. I don't want to put them because this is going to be messy and I'm going to not write the proper ones. That's almost sure. I will just point out at which point in my reasoning you need some integrability. And once you understand exactly what integrability you need in order for all the arguments to go through, you can reverse engineer everything and put whatever is needed at that point here. But there, this is really just integrability. You don't need anything else. All right. So, okay, now that I have everything, so the utility of the agent, so I keep the same notations as this morning. All right, so this is the utility that the agent gets when is offered the contract psi and is choosing the effort alpha. So I'm just calling the efforts alpha instead of A compared to this morning. But this will be exactly as before, expectation under P alpha, and then some exponential utility here of psi. So here I'm going to assume that this is salary that's perceived at the end of the contracting period. This morning it was at time 1. Now this is going to be at time capital T. And between 0 and capital T, I have accumulated cost of effort. All right? So that's, yeah, more or less the equivalent of what we did this morning. So if you take Holmstrom and Milgram's paper, C is not an arbitrary cost function. In Holmstrom-Milgram, you take C of A to be basically CA squared over 2. If you remember Pierre's lectures, if I do this, I'm in one of those linear quadratic models because I have linear dynamics, quadratic costs, and then you should expect that in this case things are going to be nice and easily computable, right? That's exactly what's going on. That problem is simple enough that actually I can solve this for whatever specification of C that you give me here. I most likely only need that C is strictly convex with superlinear growth. Something like that should be enough. If it's quadratic, I can make completely explicit computations, but even if it's not quadratic, you can still figure out exactly what the optimal contract looks like. All right, so that's for the preset, that's for the agent. Now the principal is also going to be exponential utility maximizer. And again here, you will have to solve this problem. So minus gamma p. Now I'm assuming that he gets the value of the output at the end of the contract minus the salary that he has to pay at the end of the contract as well. Right? So yeah, that's just really translating in continuous time what we did this morning. Okay, so I told you that when we started today that the important thing was when I look at the problem of the agent, given a contract psi, can I understand this set A star of psi of all the optimal controls associated to this thing here? Okay? So our first goal so we want to understand the structure of the set A star of psi of optimal controls for the agent. Good. So how do you go at something like this? So if you know a little bit of optimal control, this problem here is a standard optimal control problem, right? This is some sort of terminal reward that I have here because this is exponential utility. This is multiplicatively separable, which means I can also interpret this as some sort of discount that's appearing there. So I know many things about that problem here. I know in particular that if I extend it dynamically, this will satisfy a dynamic programming principle. Yeah. Yeah. Good. Okay, so that's a good question. So there are two answers to that. The first one is, maybe let me repeat the question in English for the people online. So the question was, if you've seen classical optimal control, and it's probably like that Pierre did it as well, you would typically here have fixed probability measure. And yeah, there should be like, if you put an X here, you would in principle have X that's indexed by alpha, and you would optimize over that. If you think about what I did this morning, I told you that I had X, that was a random variable. And when the agent was choosing an effort, what we were changing was the distribution of X. Right? In the example, when I choose A, X is Gaussian, but I'm changing the mean. So I'm not changing X, I'm changing the distribution. So I have a realization of a random variable. I don't know what the distribution is, but when I make an effort, I'm influencing what that distribution is going to be, so I'm influencing the likelihood of certain outcomes. So then, if you accept that it's a good way to specify the problem in a one-period model, then the natural way of doing it dynamically is the same. I want to change the X is given to me, I have one process, and I want to change the distribution of the process. Exactly. So now, if you think about this in terms of stochastic control, and we forget about all of that, this is what you would call the weak formulation of my stochastic control problem, while what you were mentioning would be the strong formulation. I have one fixed probability space, a family of processes indexed by the control, and on that fixed probability space, I optimize my criteria. Here I'm more in the spirit of weak solutions to SDEs where, okay, my probability space is almost fixed, but what's changing is the probability measure, right? And I'm optimizing over that. So the reasons are, historically speaking, those contract theory problems, they're written under weak formulation in the static model, so it makes more sense to do it like that. And practically speaking, it's also easier for many of the things I'm going to show you to work with the weak formulation. Most of the time, doesn't make much of a difference at the end of the day, because you would typically prove that doing what you want or doing what I've done leads to exactly the same value, provided things are sufficiently regular. Okay? So in most cases where you can just go all the way through the computations, doesn't really matter. But here it's really somehow nicer also from the economic points of view to think that what you have is, you see the realization of something, and the only thing you just seeing a path of X, you just don't know how likely that path is, right? I mean, if you see this, you know it's very unlikely, okay? Now you see something like that, you would say, this is more likely that this path comes from a realization with positive alpha. But that could also be a realization when alpha is 0. I don't know, it's just much less likely. Okay? And what I'm trying to figure out by writing it that way is what is the distribution of X that's actually coming from efforts chosen by the agent. Okay? But it would be a valid point to try to do this in strong formulation. This is not done for technical reasons, and because historically speaking, that's not what people have done. Where was I? Yes. So I want to understand what's going on here. So that optimal control problem will satisfy some dynamic programming principle. And if you've worked a little bit on that, you know that intimately linked to the dynamic programming principle, you have the so-called Martingale optimality principle, which is basically exactly what we want, because this is a principle that tells you, take an optimal control problem like this. This is going to be an optimal control if and only if some process that we will define soon is a martingale. Okay? So if you've never seen that, don't worry, I will give you not all the proof, but somehow how this works. But it's exactly what we want. Okay? So this is the tool I'm going to use at this point to understand what is the structure of A star. I will also show you at the end that everything we're doing now, in some cases, is completely useless. I'm showing it to you so that you understand where things come from. But if you're lucky in your problem, you can bypass everything that I'm showing you and basically start from the end of the reasoning and just finish exactly what you want. All right, so should be number 2. So MOP, that's for Martingale optimality principle, and A star of psi. So as usual, in optimal control problems, we're just going to introduce the dynamic version of V0A. And now you're going to understand why I've put a 0 here since the beginning. So what I will call Vt of A, this is simply the essential supremum over alphas of almost exactly the same thing as before, except that now I'm accumulating costs starting from small t instead of 0. And then, because I'm sitting at time t, I have access to information, so I'm conditioning this on ft. Okay, so that's just the time t value of the agent's control problem. And in the economics literature, this is usually called the continuation utility of the agent. And the interpretation is just that you're sitting at some time t. This is how much utility the agent can accumulate all the way to time capital T by behaving optimally. So this is the utility that it gets by continuing working. All right? So I'm not going to write down what the DPP is. I'm just going to give you the Martingale optimality principle in this case. It's a standard master's degree exercise to prove all of this. So let me put this as a theorem. I wouldn't actually know what a reference is for that. Where was this? Anyone knows where this was proved first, Martingale optimality principle? Is it already in Bellman or? Okay, that I don't know. But again, easy exercise. So if there is, let's say, enough integrability in C, all right, and if we define, so let me call this RT alpha. That should be VTA of psi here, sorry. So if you define this to be exponential gamma A integral 0 to t of C times V, then we know two things. First, for any alpha, R alpha is a P alpha super Martingale. And the second thing that we know is that some control alpha is in A star of psi, if and only if R alpha is a P alpha Martingale. Okay, so intuitively, this is not very surprising. The fact that I multiply by this exponential here, this is just so that this goes inside and this completes the integral, which now would be from 0 to capital T. And then if you just don't think too much, what do you have here? This is some sort of supremum of conditional expectations. Conditional expectations are martingales, provided that you have enough integrability. You take supremum over that, just check your inequalities, that should be a super martingale. So it's of course a little bit more complicated than that. The proof requires additional steps that I don't want to talk about. And then, of course, when the supremum is attained here, the soup is gone, and I really have a conditional expectation, so I should have a martingale. So that's the intuition. You can make this rigorous. Again, not very complicated. Just need some technical steps in the middle. All right? That's more or less clear for everyone? Okay, so now we have this. We're going to use it to understand a bit more what's going on, because at this stage, great. I had something here. I'm trying to understand what is attained, where the supremum is attained here. I've transformed this into another problem that's at this stage not telling me much more. But once we're here, we're going to be very happy that we know a little bit of general theory of processes. Because when I tell you that something is a martingale, we're in a Brownian filtration. So something being a martingale actually tells you a lot of information. So from the previous result, what I know is that if, say, alpha star belongs to A star of psi, then our alpha star is not only a P alpha star martingale, it's a non-positive martingale. So why is that? I don't know if it is still written, but VA is negative, right? It's minus exponential of something. I'm multiplicating this by an exponential, remains negative. So this is a negative P alpha star martingale. Now, because my filtration here is the one generated by a Brownian motion, you should know that martingales in that filtration have to be stochastic integrals with respect to B. And here I actually know a little bit more. The ones that have signs, they have to be stochastic exponentials. Okay? So it's actually an easy generalization of the result. And here again, I'm cheating because I know what the end results are, so it's going to be faster for me if I just write it that way. So since F is a Brownian filtration, we deduce that there is some process Z so at this stage I really don't want to go into detail, so let me just say that Z is locally in H2. And such that for alpha star T of psi, I can write it as minus, because it's negative, the stochastic exponential, okay, so let's write it completely, of, okay, here, again, bear with me for a second. The proper way of writing it should be Yes. All right. Okay, so I've done two things here. I've put this gamma A sigma. Doesn't matter, it's just going to make it so that I don't have to divide by gamma A sigma later on. It's just a renormalization that's useful for me at this stage. And then I have minus this stochastic exponential driven by B alpha star, because that's my Brownian motion under P alpha star. All right? So this is Martingale representation, and here just a renormalization, again, because I know what's going to happen afterwards. Somehow, if you want, the only thing I'm doing here, I'm putting the minus gamma A, because in the utility I have a minus gamma A that appears, so it's nicer if it's like that. And the sigma is because what matters for me is not really B, it's X, and X is sigma dB. Okay, so it's really just for that reason that I put it that way. All right? Okay, so now this actually gives me a lot of information, because now what we know is that Vt, which is just exponential minus gamma A C of alpha star ds here. So we know that this times, yeah, this is this times R alpha star. This is a nice bounded variation process. This is a Martingale. I know that this guy is a semi-Martingale, and I actually know more than that. I know that this guy is an Ito process. And if it's an Ito process, I can write down the dynamics. And so this is where now you're going to see why I did that thing here, is that because I'm not going to write down the dynamics of V. I'm going to switch things a little bit, and V is in units of utility, and I'm going to change it back to units of cash. Okay? It's just a trick that works only for exponential utility. The whole reasoning I'm showing you would still work exactly the same, except that I would lose most likely the sign thing over there, so I would just have a stochastic integral instead of having a stochastic exponential in the representation. Here, there is a little bit more structure that's associated to exponential utility, and it's better to work with what I will call the certainty equivalent instead of writing with the value function. But it's an exponential utility thing. And basically taking the certainty equivalent means more or less that I'm going to take the logarithm of that thing, which is why now you should understand why I've written everything with exponentials from the start, because I knew I was going to take logarithms afterwards. If you've already done standard exponential utility maximization, those are completely useful tricks. So defining now, I'm going to call it yt psi. So this is minus 1 over gamma A log of minus VTA of xi. So this is exactly the inverse of the utility function. Okay. So then I can just apply Ito's formula. So same thing, trust me. I've done that computations enough time to know that I will make mistake if I give you the details, but I know by heart what the result should be. So here you will be able to prove that the dynamics of this yt is exactly given by so here this is going to be you're going to get C of alpha star here minus alpha star t zt. So the z here is the one that was there. Minus 1/2 gamma sigma squared zt squared. So that's the dt term. And then here you will get minus zt sigma dB. All right, so basically what did I do here? RT alpha star, you know the dynamics because it's just a stochastic exponential over there. You multiply this by the exponential, great, that gives you an additional dt term. Then you apply Ito by taking this transformation, and if you do the computations all the way and go back to dynamics under B instead of dynamics under B alpha star, you should get exactly this. So this term is the one that comes from the discounting over there. This one here is the one that comes from the fact that I was under B alpha star and then I moved back to B, so that's the drift term that was missing. And this one here is the quadratic variation term that appears when I apply Ito to the logarithm here. Okay? I hope my signs are correct. I think they are. So basically I can prove this. All right. That's nice. Doesn't tell me much about alpha star at this stage. But actually it does. It does because we've only used one part of the result I gave you. This Martingale optimality principle, I told you two things. One was something is optimal if and only if you have a Martingale. The other one was also for whatever other control you get, you need to have a super Martingale. That we haven't used yet. So keep that in mind. That's going to be useful afterwards. But for now, we need to recall that R alpha xi should also be a P alpha super Martingale. So I know the dynamics of R alpha star. Does that give you the dynamics of R alpha? The answer is yes. Because if you just look, R alpha t is just R alpha star t times exponential gamma a. So you should get C of alpha alpha minus C of alpha star. Right? You move from one to the other just by changing the discount. So I'm adding and subtracting whatever I need. Great, I know what the dynamics of this is. Nice bounded variation process. I can apply Ito's formula again. And trust me, if you apply Ito's formula once more, we're going to find that the drift of R alpha under P alpha. Okay, again, you apply Ito, you change the Brownian motions the way they're supposed to change. You're going to get that the drift of this is okay, it's not going to be exactly, but it's going to have the same sign. So again, I'm going to use the super Martingale property. So the only thing that matters for me is that the drift has the correct sign. I don't need to know exactly what it is, I just need to know the sign. So it's going to have the same sign as the following quantity, alpha star z minus C of alpha star plus minus alpha z plus C of alpha up to the sign. So if I have a super Martingale, the drift should be, super Martingale, this decreases, so the drift should be negative, right? So if the drift is negative, then I need this everywhere. All right? And this should be negative. Okay, so the drift is not exactly this. There is like most likely a gamma A times the stochastic exponential over there in factor, but that doesn't change the sign. Okay, now if we look at this, we should be able to claim that this implies that alpha star belongs to the argmax of some function that I'm going to call h. Where h of z and a is az minus c of a, right? What I'm telling you here is that this function h, evaluated with alpha star, should dominate the same function h, evaluated at alpha, for any alpha. And this should be in principle true dt times dp almost everywhere, which, because for instance, I can take constant process is alpha has to imply that alpha star here should be a maximizer of this function given z. Okay? So there is a little bit that needs to be written properly here, but intuitively this is exactly what's going on. Okay, so that's good. That's actually giving us more information here. Now we know that if you give me an optimal control, I can find this process z, and alpha is one of the maximizers here. And I've also found out something else, which should still be written somewhere. Yes, I have this equation here that's satisfied by the certainty equivalent of the value of the agent. So if I summarize everything I know at this stage, wait, no, I can erase this. So if you give me xi a contract and some optimal effort of the agent associated to this, what can I do? First, I know that I have this equation over there that I will write the following way. So yt, y capital T of xi. What is that? So if you go back a little bit, this is minus 1 over gamma a log of blah, blah, blah. If you check this directly, dA at capital T is just minus exponential minus gamma a xi. So when I take the inverse of the utility, I get xi exactly. So this here is xi, and I also know if I integrate the equation that I wrote over there, that I can write it like this. So now inside the drift, if you look, you will see what you will see. I have C alpha star minus alpha star z. Okay? By the reasoning I've made here, I know that this is where the supremum of H is attained. So I can just write it differently and say that here this is the sup over A of A zs minus C of A. And if I didn't mess up the signs, I think plus gamma A over 2 sigma squared z squared, and plus integral 0 to t zs dxs. dxs is sigma dB. And the second point, I know exactly what A star of xi is. This is, let's say, no. What I know is that alpha star S belongs to the argmax of this function H ds dp almost everything. Right, so in particular in the case where C is a quadratic cost, the argmax here is extremely easy to compute. There is one element. Yes? It does not depend on alpha S. It depends on alpha star. That's a good point. I know there exists some z such that all of this is like that. It has to be satisfied, right? So I started from alpha star, whatever it is, that's optimal. I have it. I know that from this I can construct some process z, as we did, and alpha star and z are related, and the way they are related is through this equation. So in particular, if you want an example here, if C of A is C A squared over 2, you're going to get that alpha star is ZS over C. That's the only maximizer in the function. So that's how they're related. Okay? Of course, I mean, you see the reasoning, right? I start by something that's optimal, and I'm going to get necessary condition that it has to satisfy. I still have to go the other way around afterwards and make sure that if I give you all of that, then I do have something that's optimal in order to have the full characterization. So here I have plenty of information. You gave me a contract. I obtained this. In order to prove this along the way, I used the alpha star, but in the way the formula is written here, alpha star doesn't play any role. So basically what I'm telling you here is that given a contract, I can find this process z, and I can actually also find this constant y0, such that the contract has this form. And on top of that, I know that the optimal responses of the agent are automatically of the following form with that process z. Now, as you mentioned, all of this is great, but what's z? I don't know what z is at that stage. It's just an abstract thing that came from Martingale representation. It doesn't tell me much. What I do know is that z exists. You give me a contract, I can always do that, provided I have enough integrability and I understand what the optimal controls are. So that's what I'm going to do. I'm going to do things the other way around. My problem is that at this stage I don't know z. Z appeared from the contract. So what I want to do is do things the other way. I want to give myself z and build the contract from that. And then of course, at the end of the day, when you want to solve these problems, you don't do any of the things I showed you. You actually go directly to what I'm going to write now. I mean, you don't understand where what I'm writing is coming from if you haven't done this analysis here. But once you understand how this works, you can bypass many of the steps. So now the problem that we have is what's that z? Like, what can I say except that it comes from Martingale representation? If you do Martingale representation and you have Markovian functions of, say, strong solutions to Markovian diffusions and a little bit of regularity, then you know more about the structure of what appears in the Martingale representation. But here I'm in a very generic framework. Things are non-Markovian. I don't know much about z. So because I don't know much about z, I'm just going to choose it myself. So we're going to reverse the problem. And define I take some z in H2 log, I take some y0 in R. I'm going to define now a process yt, y0, z. And what I'm doing, I'm just going to mimic really what's going on there. Oh. Okay, so I define this process. Okay, and here this is really just a stochastic process, starts from y0, okay, and I have this z that's appearing in the dynamics. Again, I am exactly mimicking what's going on there. And now, I'm again going to cheat a little bit with integrability conditions that I'm not detailing. And let's call calligraphic z the set of z's such that if I take now the value of this at capital T, this thing here belongs to C. So this is an F capital T measurable random variable, all right? So it's acceptable as a contract. Of course, I told you that implicitly here I should have some integrability conditions. So if I define this that way, all the integrability that I want to have on the terminal value here is implicitly encoded into Z. So I'm just telling you, take it so that I have this. And now we define let's call it, I never know how to write that letter. It's like this. Or let's call it C like this. So this C, this is the set of contracts of the form yt y0z with z here and y0 greater than this here. Okay, so what happened here? Now I'm looking at an extremely specific class of contracts. They are terminal values of this forward stochastic differential equation, which is not very differential because there is no y on the right-hand side. I take z here such that I have enough integrability, and the y0, I take it greater than this. Where does that come from? Remember R, that's the reservation utility of the agent. Now, if we start thinking about this, what's going on here? If I go back to this value, what is the y0? This is y0 of xi. y0 of xi is the certainty equivalent of the agent's value at time 0. For an admissible contract, this should give the agent a utility that's higher than the reservation utility. When I'm putting this constraint here, this is exactly what I'm saying. I'm saying that the initial value of this process, I'm hoping that and I'm going to show that tomorrow, no, not tomorrow, on Thursday, that if I offer that contract, the utility that the agent gets is exactly y0. So I'm just putting the constraint that reservation utility, he gets at least that. It's exactly to take care of that I'm putting this here. Okay? So, yeah, let me just write the theorem. And then I'll stop there. The theorem is that this set of contract is exactly equal to the original one. That if you start with some small y0 and z, and you offer that to the agent, the utility that the agent gets is, the certainty equivalent of the utility is small y0. And what is the optimal control of the agent? Well, it's anything in the Rmax of h evaluated along the z you've given yourself. So the theorem is that this is equal to this, and for any z here, yeah, we have so the utility that the agent gets when we offer this contract here is exactly equal to this, right? So this is the certainty equivalent, so the utility is the utility of this. And I know exactly what the set of optimal controls for that contract is. I don't like writing it that way, but okay, let's make my life simpler. Take C to be quadratic. Okay? Doesn't really matter, it's just going to take me longer to write the general result. So if C is quadratic, I know exactly what this is. There is only one optimal control associated here, and that's this one. I didn't want to write the general case because in general, if there are potentially several maximizers, then the optimal one are any nice measurable selection of the argmax evaluated along Z. So it's much easier when there is only one. Okay, and this is great for us. This result is great because it's basically telling us we started with that general class C of contracts, and we proved that there was no loss of generality in actually looking at something that seemed to be much smaller, that is the class of contracts that are terminal values of this forward process that's written over there. Okay? So what we showed is that, yeah, no, doing this actually covers all the possible contracts I want already, which is one thing that's good, but more than that, for that specific class of contracts, I know exactly how to solve the problem of the agent in the sense that I know what A star is. And when I do it that way, it's much better than the previous way, because now I know what Z is. I've chosen it myself. So I choose Z, and that gives me exactly what the optimal effort of the agent is going to be. So that I will prove it, because that's extremely short and easy to do. And then I will show you now, we spent a lot of time understanding what the agent is doing. We've understood what the set A star was. And we're going to see now that for the principal now is not going to maximize over this set, it's going to equivalently maximize over this one. And we're going to see that now that we have this structural form, we're going to be able to solve the principal's problem by hand. And then I will explain to you some of the generalization we can do with all of that. But yeah, let's finish now. Thank you.